All right, well, I'd like to finish up here with what we started the other day on artifacts. It's probably take about 15 minutes to go through, and the topics that we have coming up relate directly to that. So that'll be nice segue. As you recall, we left off talking about EMF, electromotive forces, and muscle tension, and how they can disrupt a signal. And I showed this signal here of a poor test connection. Now
we don't see your screen, Richard.
Okay.
Richard, yeah, share the screen.
There we go. Thanks.
Yep, perfect.
Okay, so there's the this is a home training screen. So this person was in a building, actually at Yale University, at a dormitory building, and she was doing home training. And as you know, when we train like this, we can see what they're doing, over the cloud with our software. And she was getting too much high beta, so we contacted her and said, we don't think that your signal's correct, because her beta was all up around 10 microvolts or higher, 12. And so we contacted her, and Jordan spent several phone sessions with her trying to get at it, and they could never get past this fuzzy pattern here. So even the text can get a little bit stumped sometimes. And we just had a woman in Australia, no matter what she did or where she went, she couldn't get a good signal. So she was convinced it was something wrong with the amplifier. That's very rare. Most of the time when you have these problems, it's about getting a good connection or about interference around you. I mean, the Brainmaster amps, R amps, ThoughtTech amps, they're very well put together. There's not a lot of moving parts. There's not a lot of parts, period. And they don't break down very easily. Most of the time when you're getting a crummy signal, the amp is working. There's not a problem with the amp. It's usually how you're hooking up. But when people are new, they're intimidated, they're confused, they don't understand electronics. So sometimes maybe they're just not the right candidate if they don't have the patience to learn to get a good signal for learning neurofeedback. This person training at home, though, she understood a little bit better what was going on. And so we had her pick the amplifier up off of the desk. This is something that you can really do quite often to check to see if it's local EMF. And so she picked it up off the desk, and the signal suddenly went to look like this. So we went from that, you can see how fuzzy that is, that fuzzy line, biphasic with all those sharp, pointy, looks like sawtooth waveforms, and now you can see it's kind of clean. Looks like it was written with a fine pen. And it's got smooth lines. So you can just kind of look at the difference there. So she picked it up, and that looked like that. So we knew that there was EMF locally, or dirty electricity, that was affecting this. We had tried all of the strategies, but that's kind of one that people don't really know about typically. So we had her move to the other side of the room, and she continued to get a good signal. And then we asked her to look under the desk, and there was a router and connections under the desk, and a lot of plugs plugged in. So she apparently had a combination of dirty electricity and EMF affecting the signal. And so once she moved to another side of the room, she was able to do the home training much better. So the kind of headache you can sometimes get with home training. So there's the comparison between the signal with the EMF and dirty electricity and the clean signal. And in fact, they often look very much alike to EMG. If you were gently clenching your jaw, you might get that kind of pattern too. But usually the EMG is bigger in amplitude. So there's another example. So what's happening if you're clenching your jaw, here's a picture of the distribution of the muscle tension. Usually it's around 150 cycles a second. At the bottom you can see 0 to 180. Around 150 is the more typical, but this was a a large muscle they were working with, the frequency was lower, and you can see it was peaking around 50 hertz, close to the 60 hertz thing. So this would be very hard to figure out whether this was muscle tension or electricity, except for the fact that if you put it on another person right away in the same room, it would disappear. You can see that the muscle tension has subharmonics. We talked about that last time, that go down as low as below 20 hertz. Actually, can go down to 13 hertz. And when you look at the brain map, you can see that it's muscle tension because you've got high beta at T3, T4, and it's also T3, T4 in beta. And that's often a hint, a clue that this beta is coming from muscle tension. And that's why we have the high beta maps in there. Not so much because we're trying to get gamma or anything, because most of the equipment you're using is not very good at getting gamma. You use special lab equipment for that. But when you have high beta and you see it reflected in the beta, you can be pretty sure that that beta is going to be muscle tension. Something to keep in mind. Your body carries electrical noise. When you're in a room, there is electrical activity moving all over the surface of your body. This is through capacitive coupling, and they have an example here. It says the power line, and there's the person, and there's a little funny-looking symbol on his head. That's a electronic symbol for capacitor. That's the EMF goes right through the air, and your body is a conductor. It's a crummy conductor, but your body picks it up. Your body has different levels of conductance. It's resistant, and it produces what we call a complex variable magnetic field, which induces a voltage across your skin. So displacement current from the wiring encounters your body's impedance or resistance, and that generates a voltage in your body on the surface, and it's all across your body. And you don't feel it because you're not that well grounded. I don't know if you remember seeing stories of Tesla. He would stand on a cork pad or something that isolated him from the ground, and he would hold a wand, and he had a giant generator of electricity next to him, high-frequency electricity, and it would jump into the wand or paddle and go right across his body, and his body would glow, and you got a glowing halo, and people would ooh and ah. The voltage was really high, but there was no current, and the current wasn't going through his body. So that's what's happening to your body all the time, and you hear Martin talking about electromagnetic fields, and he's not joking or talking about something subtle. It's something very strong. In fact, I don't know whether Cindy Kingren or somebody who was listening at the time said she took out a fluorescent light and went and stood under the power lines in the back of her house and held it up just because she heard that would make it glow, and she didn't believe it, and it actually glowed. And she's like, oh my God, there's so much voltage in the air when it hits something like one of those fluorescent lights. It'll actually light it up. So in a building, your body is getting bombarded with all of these different electromagnetic waves, and they're moving across your body. And that's why if you don't have a ground and you're not grounded to your amp, you'll get all of this crazy up and down voltage on your screen. And that's one of the reasons you need to get the ground, your body, and the chassis and the amplifier, which is where all the components are grounded. They all have to be at the same level and getting rid of any excess voltage. So this voltage in your body produces voltages in your into the sensors, and your amp picks it up. And so that's the general nature of how this stuff works. And so right here is the technical side of it. Capacitive coupling between the power line and the measurement leads in the human body. The displacement current in the human body is C, and you can see right there, that capacitor. Coupling capacity between the power line and the human body. Then the displacement current in the measures is Z1, and you can see them there. These are little resistors producing voltage. It's your body's resistance. The impedance of the body between the two electrodes and the impedance of the electrodes. So they're giving resistance. And then the impedance of the ground, because you're not very well grounded, at ZD. And then the differential input impedance of the instrumentation amplifier, Zn, so that's at a different impedance or resistance. And then the input impedance of the instrument amplifier itself, and then the coupling capacities between the power line and the measurement lead. So you're getting induced voltage into the leads going from your amplifier to your body, and it's being generated the same way as in your body's surface. So not only is your body picking up this induced voltage, but the leads from your amplifier to the skin is picking it up. And they're all at different resistances and different voltages. So you can see it's a pretty messy environment you're trying to collect information in, and you're trying to get millionths of a volt. So it's almost a miracle that we can get this to even happen. Now, what happens on the body when it has this resistance or impedance in the sensors is it creates what's called a DC offset. Your body's producing DC current. It's not like up and down current like your brain. It's just a constant steady flow of maybe, 50 millivolts or something like that, or 30 millivolts. And it's just constantly coming across your body. It's there all the time. And so what you're trying to do with the amplifier is measure the impedance there, resistance in the sensors, and make sure that it's not too high. If it's too high, the amplifier won't pick the voltage up correctly. You'll get incorrect readings. Now, Brainmaster was using offset for the discovery, and they still have that. If you don't have the impedance lid, then you're using the offset. When you see those little numbers, offset, that's what it's talking about. It's talking about the voltage that's being produced in the sensors and the impedance that results from all of that. You have to match the impedance correctly between the sensors and the amplifier, or you won't get the correct voltage readings. So DC offset, when they did research on it, is not a good measure of impedance. It doesn't mean that DC offset is not useful or not valid. It just means you can't use it to estimate impedance very effectively. So you do want to get your offsets as low as you can, preferably below 30 on those on the Brainmaster, but it's not the same as impedance. You're measuring the actual offset. So changes in the skin potential can increase the DC component of the signal from the scalp. So here's the zero line, and you can see let's say that's a brainwave going up and down. Well, the DC component can shift the average voltage. This is producing an average voltage of 0 of the signal, so the AC component shifts above or below the zero line. So that's what's happening here. This is at 0, but there's a DC component that's adding into the AC, and it's shifting it above the zero line. So there's a steady voltage here. It could be 1 microvolt, 2 microvolt, 3 microvolts. It could be 50 microvolts, but there's a DC current shifting it up. Most of the amps that we have filter out the DC component, so this doesn't happen. And we talked about that in the last presentation where I showed you how a transistor worked and the fact that we would filter out that DC component using what we call a capacitor. So here's the components of DC offset. That's electrode-tissue interface. When you put a sensor on your skin, this is what you're dealing with. There's a voltage potential between the inside and the outside of the skin, and there's ion movement through the skin. Okay, that creates a current and a voltage. The dead skin on your body, and everybody has a layer of that, increases the impedance. Can make it 2 mega ohms or higher. The voltage potential, there's a voltage potential between the skin and the paste. So when you put the paste on, this starts up a voltage potential and an ion flow between the skin and the paste. And between the paste and the electrode. Okay, so now you have all these different, they're like little batteries adding up these voltages. And then you have increases in sweat gland activity. They can increase or decrease the DC offset. And then there's movement between the metal sensor and the skin, and that can increase the voltage, the DC offset. So this is why you have to have a lot of paste on your sensor. If you don't have enough paste on your sensor and the sensor's touching the skin and it's pulling back and forth, that's going to give you a variation in your voltage reading and give you artifact. When it's on the paste, that slight movement back and forth of the sensor doesn't have that effect. So that's one of the reasons why your paste is your friend. Now the DC offset, when you add it all up, is usually, 20 to 50 millivolts. That's trying to get in your sensors and in your amp. And you only want to measure like 50 microvolts. This is 1,000 times larger than your EEG signal, this offset that your skin is collecting from everything around you. So now maybe you can see why you're getting so much trouble sometimes if you don't have enough paste and you don't have the skin, pretty clean, and you don't have everything on there. You're not going to get a good signal because you're going to have all this voltage on the skin is going to create a change in the impedance of the sensor there. And if that impedance gets too high, then your amplifier starts reading the voltage differently. And on top of that, the active and reference are both feeding into the amplifier and the input in the amplifier. If there's a difference in those, that'll create even more of an inaccuracy in what you're reading. So here's just an example, and we're getting close to the end of this. So if you're getting overwhelmed with the technical side, just listen to this a couple of times and think about it. I'm trying to keep it pretty basic because it's very complex. This is, of course, network and component diagrams here, and they always, you look at those and your eyes cross and say, oh, I don't know what that stuff is. It's really not that complicated. The wiggly line is resistance. It tells you how much skin resistance is. The wiggly line with this other thing is telling you the impedance in that area, and this little area here, that's energy, battery, ion movement, and current movement. There's that R again. So the gel has resistance, and then this again, the electrode produces an impedance. So the impedance is made up of all of this stuff in the skin. And on top of that, you have sweat glands in the skin. And when they fill up, that shifts the potential from positive when it's low to negative when it's high. So when you have somebody in the chair and they're upset or excited and the sweat gland activity increases, that skin conductance you're measuring, that can dramatically shift the DC component of the offset and increase the impedance and mess with your voltage and give you improper readings, shift the voltage up and down, and it'll be false information you're getting. Now, fortunately, most of the amps, like our amp, is DC coupled to the skin, and like Brainmaster is DC coupled to the skin. So it takes in all of the information, and it uses the digital filters, uses algorithms in your computer to differentiate the DC from the AC and filter it all out. So that's one of the reasons we can read infra-slow and infra-low subtle shifts, because you can actually calculate them in the computer. But it is interesting to note that people getting upset or excited can alter their skin potential, change their DC offset, and potentially change the voltage on your amplifier. So you want your amplifier to be really high impedance input and the skin to be as low as you can. But since amplifiers are now in the really high ranges, things have changed since the 90s, although most of the old guard neurofeedback don't know much about electronics, and they don't understand this stuff, and they keep saying, "Oh, you got to have it below 50 k ohm," and a lot of people in the medical EEG are old timers, and they're still thinking the same way. It's surprising. I mean, remember, we were just talking about how medical doctors are 17 years behind the medical research, and that was published in Scientific America. Well, the same thing occurs in our field. A lot of the old guys who never really learned electronics are really behind on understanding this stuff, and they're still screaming, "Oh, you got to have it at 5 k ohm." That creates problems with hygiene and pathogens and so forth. Removing the dead skin decreases the impedance and enhances the power transfer of the amp, and that's why they were always saying, "Oh, you got to rub that skin good, get it really clean," and so forth. But modern amps no longer require impedances below 5 k ohms because the amp impedances are very much higher, and the high electrode impedances reduce the common mode rejection efficiencies. Okay, so the impedance of the electrode must be lower than the impedance of the amp, and this is a diagram showing the amp and the source, the skin and the amp. And high sensor impedance results in a loss of power transfer. In other words, if the skin gets too high in the offset, you start to get the wrong voltage readings on the amp. Impedances up to 40 k ohms, kilo ohms, are fine. If you've got impedances at 40, in fact, it can be higher. So now I'm going to cite somebody as far back as 2001 where they actually did laboratory experiments, and we're just people around workshops, citing old ancient literature on electronics. In our experiments, using an amplifier with input impedances of 200 mega ohms, and ours is like 500 or 800 mega ohms, and BrainMass is like giga ohms. So there was no significant attenuation in any of the standard EEG frequency bands. Circuit analysis suggests that for this input impedance, scalp electrode impedances up to 200 kilo ohms still allow for accurate signal acquisition with 0.1% error. So, Thatcher has said it, I've said it, you can go up to 100 k ohms and it's fine. And the research actually shows 200, and with input impedances like we have in our amplifiers today, it can go even higher. So you don't need to really abrade the skin, technically. You could just, most of the time, just put paste on there and you'll be fine. And you'll still get a good reading. And as long as you're getting a fine, nice, clean line, you're getting good impedance. The only problem is that if your connection is too crummy, you'll start getting a lot of fuzzy line, and that's because that capacitance is changing between you and the surrounding environment, and you're getting more voltage on the skin because of you're changing the nature of the connection. And again, thanks to Dr. Morella for any of the EEG artifacts that we showed. Okay, so that's our story, and we still have lots of time to talk about other things.